I will speak about quantum gravitational effects on scalar and tensor perturbations during inflation. This is a work done in collaboration with Klaus Kiefer and Manuel Kramer. So there are many different approaches to quantum gravity, and inside each of these approaches, there are many different ambiguities and choices one makes to construct a theory. Therefore, it will be really nice and really helpful to have some testable predictions, to have some experimental guidance to construct a theory. One of the most promising scenarios for such testable predictions will be the inflationary phase of the universe. Therefore, the idea of the goal of this talk, of this work, is to obtain quantum gravitational effects to the power spectrum of the scalar and tensor perturbations. This is more or less the outline of the talk. I will be using the framework of geometrodynamical quantum gravity. This is probably the most conservative approach to quantum gravity. And even if it might not be a fundamental theory of quantum gravity, it should give us some idea or some estimations at certain level. So we'll be dealing with perturbation on a homogeneous universe with a scalar matter field that will be our inflaton field. We'll construct master gauge invariant variables to describe these perturbations living on that background. And then we'll quantize both the background and the perturbations all in the same time, making use of a Wheeler-DeWitt type of quantization. Then we'll arrive to a master Wheeler-DeWitt equation, and there we'll apply a Bohr-Oppenheimer type of approximation. We'll make an expansion in Planck mass, and then at each order we'll recover the different equations. At first order we'll recover the classical Hamilton-Jacobi equation, which will describe the classical dynamics of this system. At next order we'll find a Schrödinger equation that will be equivalent to quantum field theory on this fixed background, classical background. And at next order, we'll obtain a correct Schrödinger equation that will contain what we'll be interpreting as quantum gravitational corrections. At the end, we'll apply all these things to the de Sitter case. So let me start just giving a brief review of perturbation theory in general relativity. The idea is very simple. We have a background metric that describes space-time, and on this manifold we put some perturbations that are described by this h mu nu tensor. Then the axiom of general relativity with scalar matter field is given in this way, in its Hamiltonian form. We have these two kinetic terms. The first one this is the spatial metric, where Latin indices stand for spatial indices. And this pi I will be the conjugate momentum of the metric, which is related to the extrinsic curvature. Then we have here the scalar field and its conjugate momentum. And here we have the Hamiltonian, which in general relativity is a linear combination of constraints. That can be written in this way. The lapse times the Hamiltonian constraints plus the shift times the deformation constraint. Then the first variation of this action, the equaling to 0, extremizing this action, will give us the background equations of motion, the Einstein equations. In particular, if we take variation with respect to the lapse and the shift, we obtain the 4 constraints of general relativity. Now I want to find the linearized equations for this tensor, for the perturbations, and this can be done by considering the second variation of the action, which provides an action functional for the linear perturbations, and can be schematically written in this way. Okay, where I have defined here the P, this P is the perturbation of the pi momentum, and the H is the perturbation of the metric. Okay, and the other are just left indicated. Then taking variation of this action with respect to the perturbative variables, we obtain the linearized equations of motion for the perturbations. In particular, taking variation with respect to the perturbation of the lapse and the shift, we obtain the constraints that must be obeyed by the perturbations, which are exactly the linearized constraints. So at a classical level, usually we see this in 2 steps. We first solve the background, then the background equations, or the background functions, are plugging it here in this action. They are non-dynamical anymore, and we use this action to obtain equations of motion for the perturbations. But since we want to quantize everything, then we need an action, a total action for all the system, and we obtain this just by adding the background action plus the action corresponding to the perturbations. Then this is our total Hamiltonian, and these are then our 8 constraints. Okay. So now, in order to perform a quantization of this system, there are different ways to follow. One will be to quantize a la Dirac. That will mean to quantize, to construct a Hilbert space and the wave function, and then promote all these constraints to operators, and we will request that the action of these operators on the wave function to be vanishing. Okay? This was done, for example, by Halliwell-Hawking in a very well-known paper with a Freeman-Robinson-Walker background. And in this way, one obtains many equations that it's really difficult to deal with. Another idea, another possibility is to fix a gauge, to solve one or several of these constraints, and afterwards quantize. And another third way, at least for the perturbative constraints, is to construct master gauge invariant variables. Let me just explain very briefly how this is done. We'll assume vacuum for just to explain the general procedure. And this is just for this slide, I introduce the notation of these capital I and J indices, which goes from 1 to 6. Okay, we have 6 components here, 6 degrees of freedom, 6 couples that are denoted by this, and they obey certain Poisson bracket. So the 4 linearized constraints are the generators of the perturbative gauge transformations. And then the idea is to perform a canonical transformation to a new set of variables, these tilde variables, so that 4 of the new moments are equal to the constraints. Okay, so that the constraints take really a very simple form. If one is able to do this, then one will have achieved the decoupling between the gauge and the physical degrees of freedom. Okay, this can be seen very easily because the h tilde 1 to h tilde 4 variables, these are gauge dependent. If we take Poisson brackets between this and the generators, they are non-vanishing. On the other hand, the p tilde 1 to p tilde 4, these are the constraints themselves, which are gauge invariant because they commute with themselves, but they are constrained to vanish on shell. Okay? So then we could just take these variables equal to 0 and forget about them because they're just gauge modes. In this approach, if we didn't make them equal to 0 and we quantize them, the issue will be that this will be promoted to an operator that will be the derivative with respect to each canonical variable. For example, p tilde 1 will be promoted to the derivative with respect to h tilde 1, and this acting on the wave function should be 0. So this will tell us that the wave function should be independent of the h tilde 1, h tilde 4 variables. Okay? And at the end, we have these other 2 couples, the 5 and 6 couples, which are gauge invariant, they commute with the commutators. And besides that, they are master in the sense that the complete perturbed metric can be reconstructed in terms of them. Examples of these master gauge invariant variables are, for example, the Regulian Serili functions in Schwarzschild background, or the Mujano-Sasaki variable we will use now in our cosmological background. So now we'll consider then the Freeman-Robinson-Walker metric written in this form. In this homogeneous case, since the lapse is equal to 0, the shift is equal to 0, because we have taken adapted coordinates, the only constraint left will be the Hamiltonian constraint. This is the only one that we have to promote to a quantum operator and request that the action of this operator on the wave function should be vanishing. The perturbations are decomposed into scalar, sector, vector, and tensor components, as is usual in cosmology. And we end up with 3 master gauge invariant variables describing the complete physics of this problem. The first one is the Mujano-Sasaki variable, which describes the information in the scalar sector. And the other 2 are in the tensorial sector, which is automatically gauge invariant because the gauge generators do not have any tensorial components. And these are the 2 polarizations of the gravitational waves. I also named them by a V, lambda, with this plus and cross. In this way, the constraint, the Hamiltonian constraint, can be written in this way, okay, where H naught will be the Hamiltonian of the background mini superspace model, and Hs and Ht will be the Hamiltonians of the scalar and tensorial sector, which has a very similar form, and both are Hamiltonians of parametric harmonic oscillators. Okay. So this is quite a standard, so I will jump this. We just promote that operator, that constraint to a quantum operator by the regular quantization, and we end up, we also request a product ansatz for the wave function, written in this way, and at the end, we obtain an equation for each k Okay, we have done also a Fourier decomposition. For each k mode, for the scalar sector and for the tensorial sector, we obtain an equation like this. Okay, this is the equation we have to solve to obtain the wave function. The only difference between the scalar and tensorial sector is encoded on this frequency. Okay, for the scalar sector, it's a little bit more complicated. We have the set function that is given in this way, in terms of the scalar factor and the scale factor and the scalar field. Whereas for the tensorial sector, we have here just the scale factor. So now what we're going to do is take this equation and make the semi-classical approximation. Okay, we'll write the wave function like this, and we will expand the exponent into a power expansion in terms of the Planck mass. Then we plug it in the equation, and at each order we obtain different things. Okay, at the higher order we obtain at fourth order that S naught should be independent of the perturbation. We obtain this equation. Okay. At next order, we obtain the Hamilton-Jacobi equation for this S naught, okay, which is telling us that S naught should be the action of the background space-time. This is completely equivalent to the Friedmann equation, so this is giving us the classical dynamics. At next order, we obtain a Schrodinger equation written in this way, with this psi naught is defined in terms of this S1. And this is equivalent to quantum field theory on curved spacetimes. This is the completely equivalent to that approach, and with this we will obtain the usual power spectrums. At next order, we obtain a correct Schrodinger equation that is written in this way. Okay, you see here we have the time derivative, here we have the part of the Schrodinger equation, and here we have the correction terms. These are the terms that we will interpret as quantum gravitational corrections. The problem with this term, as you see, this is a linear equation for psi 1, but this term that is multiplying psi 1 has certain imaginary terms. And this produces several problems. Okay? On the one hand, it produces non-unitarity, so we don't have an ambiguous framework in order to take expectation values. It also gives an inconsistency in the equations, which is related to that. It also gives exponentially amplified oscillation towards the past. We have just researched numerically this thing, and it doesn't allow, therefore, for the same reason, to have a Bunch-Davis-like initial data, where the modes will be oscillating with a constant amplitude of frequency at the very early times. So the only idea we have right now, because this is ongoing work still, is just to remove these imaginary terms and to construct with the remaining terms an ambiguous framework where we can take expectation value and construct the correction terms. So at the end, we take also this form for the Gauss for the wave function, and we find that the power spectra is just given in terms of the real part of this Gaussian width. So let me just show you very briefly what is the equation that obeys this capital omega. This capital omega obeys this equation. At zero order, this omega square appears here is the same as the one coming from the perturbations, whereas at first order, it has this form, it has certain correction terms, and again here, imaginary terms appear. Dropping imaginary terms in the corrected Schrodinger equation is equivalent to dropping imaginary terms from this frequency. Okay? In fact, this equation can be written in this way in terms of this y function, and you see here why, if we allow for imaginary terms from this frequency, this will produce exponentially damp or amplified oscillation depending which direction of time. So we have solved this for the zither. Okay, the zither can be obtained in this framework just by freezing the scalar field to a certain value. For both, in this case, for both scalar and tensor modes, we have the same frequency. Okay, and then we have solved the Schrodinger equation, the uncorrected one, analytically. We impose Bunch-Davis vacuum, which in this context means that the capital omega should be constant, equal to the wave number, as eta goes to minus infinity at the beginning of inflation. And in this way, the usual power spectra are obtained. Then for the corrected Schrodinger equation, I will jump this, we solve the equation linearized, because the complete equation is quite difficult. And this is the corrected power spectra we obtain. Okay, so this will be the uncorrected power spectra, and then we obtain a term that is added, so we have something positive adding to the uncorrected power spectra that goes like 1 over k to the cube. Okay, so it's more relevant for large scales. So let me just conclude. We have worked with perturbation theory on free Maranello Walker background with an inflaton field. We have constructed master gauge invariant variables. We have quantized both the background and the perturbations, making use of a quantum geometric framework. We have found a master Wheeler-DeWitt equation, and there we have applied a Bohr-Oppenheimer type of approximation. In this way, we have obtained different equations of different orders. The higher order, the one we have obtained, is the correct Schrödinger equation with certain imaginary terms, which are really painful and give a lot of problems, which are listed here more or less. And then we have analytically solved the equation, the correct Schrödinger equation, linearized, and we have obtained the power spectra for both tensor and scalar modes. We have found at the end that the power spectra is enhanced by the quantum gravity effects. Okay. Thank you very much for your attention.
Thank you. Questions?
Very interesting. I would like to ask you, maybe to other people in the audience, if you believe that in this framework maybe the distinct bump that is present at low L multiples actually in CMB can be reinterpreted in this framework. Is it possible, or it's quite difficult in your opinion?
I don't know.
Because there is this line that this is this bunch that this is distinct. It's still in the data and is out of predictions. It could, of course, it could be a systematic.
But I think in that region the data is also quite wide. I think many different things will enter there. Some oscillations on certain announcements.
Is with respect the best fit?
Yeah, so it's difficult to say. Yeah.
Other questions? Can you show this equation with the imaginary term?
This one?
Yeah. So why is it it's E times d over d eta, which corresponds to a self-adjoint operator, I guess.
Say that again, sorry? E?
This I is with d over d eta, so it is, the combination is a self-adjoint operator. So why is it non-unitary, or is it the ordering of different terms?
But it's not just this I that goes like there. This psi naught is also a complex function. So you are not only getting imaginary terms from this side, also from here.
Okay.
Yes, psi naught in both sides. Here is Hamiltonian acting 2 times on this.
Yeah. So but is that a general consequence of this kind of perturbation theory?
It's a general consequence of this framework, of this way of approaching to this problem. This is quite general, this equation. And it appears there,
So there could be other models. It's not just in cosmology, but if you apply the approximation to something else, it could also happen. And
exactly. You
might really maybe know better what it corresponds to in terms of physics or different solutions.
You mean if you plug it in for another background, for example, something like that?
Yeah, or just a completely different system, quantum mechanics.
You could do that also, In that case, the issue is that you need something like the Planck mass here that gives you to make the expansion. So in other systems, I don't know if you will have this Planck mass over there. This is
some large parameter, I guess.
Yeah, you might have some other parameter,
Okay. Yes, we have to move on to the last talk. Thanks.